Today's lecture will be on Newton's laws and the different types of forces. I'm Mrs. Estock. Let's get started. In physics, we define a force as either a push or a pull. Not a super technical definition, but at the scale that we work with forces, a push and a pull is a sufficient definition for what a force is. And in physics, a push or a pull makes no difference. They're both the same thing. In either case, a push or a pull has the ability to cause a change in the state of motion of an object. Now, a force will not always cause the change in the state of motion of an object, but it has the ability to. An important difference to make note of. As far as types of forces we will see in class, there are two main categories. The first being a contact force. The definition is just like the name implies. It is a force that requires direct physical contact to have an effect. For a contact force, there must be a point of contact between the two objects. For example, if a table is pushing upward on a book, which we will in a minute define as the normal force, then the table must be in contact with the book. In other words, the table is touching the book, and since those two objects are touching one another, that is a contact force. So they have to be touching or in direct physical contact with one another. So that is one type of force. The other type, you could guess, would be a non-contact force, or what physicists call a field force. Field forces can act over large distances without direct physical contact. For example, the force of gravity or weight force is a field force. It's a force that arises due to Earth's gravitational field, hence the name field force. So any force that arises from a field, like the force of gravity and gravitational fields, or electric attraction or repulsion from electric fields or magnetic fields, plus and minus attract, or south and north ends of magnets attract, those types of forces are due to field forces. So a field force can be exerted even if the two objects are not in direct contact. For example, the sun can pull on the earth with a force of gravity, but the sun is not making direct physical contact with the earth. So these are forces that act over long ranges or large distances. So every force I'm going to mention from this point forward will fall into one of those two categories, either a contact force or a field force. First, let's go through some of the contact forces we'll see in this unit, starting with what we call the normal force. In math class, and now in physics class, normal means perpendicular. So the normal force must be perpendicular to something. Well, it's actually perpendicular to the surface an object is touching. So anytime an object is making contact with a surface, the force of that surface on the object we call a normal force. It only exists when there is a surface in direct contact with the object. In class, we might see this as a table, the floor, an incline, the wall. Any surface we call a normal force. And as the name implies, we always draw it perpendicular to that surface. Another contact force that we will see is the force of friction or friction force. Broadly, friction is a force that opposes the motion of an object. That means that it always points or acts in the opposite direction that an object is moving. So if this polar bear here is sliding to the left, friction is working against it by pushing to the right. Well, where is friction? Imagine if you placed your hand on a rough, bumpy surface and you try to drag your hand across that surface. There's a force there that's making it harder for you to move your hand in the direction that you want to drag it. What is that force? It must be a frictional force, and it's working in the direction opposite that you are trying to pull your hand. A certain type of friction that we will now talk about is the force of air resistance. This is a form of friction that's caused by an object colliding with air particles. And anything that could change the rate of collision with the object and those air particles can affect the amount or size of the air resistance force present. So things like the speed of the object, its size or surface area, or the density of the air could cause a change in air resistance. So, in other words, objects that are moving fast or large in size, those are going to have significant air resistance. Sometimes you'll see this force referred to as drag force, but it's just a different name for the same thing. Another contact force that we will see is tension force. Tension is a force that's transmitted through a string, rope, wire, or cable that is pulled tight. So any of those types of materials, like a string or a wire that's has tension on it, that's pulled tightly, we call that a tension force. A spring force is obviously the force of a spring, but that spring can either be stretched or compressed as long as it is storing some elastic potential energy. And it can also just be an object that is stretchy. So not necessarily a string, but maybe you have a bungee cord or an elastic rope. So this differs from the tension force, and then that rope can be stretched or compressed. And then the last contact force we'll talk about is the applied force. An applied force is what we call a force that's exerted by a person that's pushing or pulling on an object. Also, this is kind of the catch-all force. So if you're trying to categorize a force and it doesn't really fit into any of the previous categories, you can call it an applied force. It's kind of the catch-all. If the force doesn't fall into any of the other category types, it's okay to call it an applied force. So those were the contact forces. As far as field forces go, there will be two types of field forces that we'll talk about in this course. One is the weight of an object as a result of the force of gravity. This is caused by a gravitational field, and any object with mass is affected by gravitational fields. The other type of field force that we'll discuss later on in the year is the electromagnetic field created by moving electric charge. So any moving charged object will create a magnetic field. And when you have two electric charges or two objects that are magnetized interacting with one another, they can exert forces on each other. You've heard before opposites attract, likes repel. That's kind of referring to that electromagnetic force. And both of these are called field forces because they can be exerted without direct physical contact. So in both cases, the objects don't actually have to be touching to experience these types of forces. So just to summarize, we have two different categories of forces, contact forces and field forces. Contact forces are when an external object exerting a push or a pull is the result of some direct physical contact. And we went through some examples. Normal force, tension force, spring force, air resistance, friction, and applied force are all types of contact forces. Whereas field forces, or non-contact forces, do not require direct physical contact and can act over large distances. Examples include gravity and what we'll refer to later as the electromagnetic force, but you could kind of separate them as magnetic and electrostatic forces. So in order to keep all of these kind of arranged in your head and be able to consider all of them, when looking at a force problem, one way to approach this, always just think about the interactions that are going on. So if you're trying to figure out what forces are being exerted on this object, just ask yourself, how is the object interacting with its surroundings? Are there any points of contact? Does it have mass? Does it have charge? Is it moving? How is it interacting with its surroundings? And we'll start to summarize this idea with something that we call free body diagrams. A free body diagram is a picture where you draw all of the forces that object is feeling. So this does not include the forces the object applies to other things. It's very kind of egocentric for that object. It's only the forces that that object is feeling at that moment. And some tips for drawing these free body diagrams. Identify your points of contact. So if there's anything touching the object, it's exerting a force. So in this example that I have here, the box is touching the ground, so there has to be a normal force. It also looks like it's being pulled by a rope, so we can call that a tension force, Ft. And if it's being dragged across the surface, there's probably some rubbing or scraping that's occurring there, so there's going to be a force of friction that's opposing that motion. And then you also have to identify any long-range forces. So if this box has mass, then it's probably going to have weight. So we're going to have to draw that downward weight force to account for the long-range force of gravity. Let's try out a couple of examples together. A book sits on a table. What forces are acting on it? So in this case, we're drawing a free body diagram for the book. So we have to think about any force that the book is feeling. Well, is there anything making contact with the book? Why, yes, there is a table underneath the book. So that upward force, wrong way. That upward force we call a normal force. It's a surface pushing on the object, and we draw it perpendicular to the surface. So we're drawing it perpendicular to the tabletop. That is the only point of contact for this object. So now we think, are there any long-range forces or field forces acting on the object? Well, since it has mass, there must be a force of gravity pulling the object downward. In our next example, an object slides down a rough inclined plane. In this example, the object must have weight, so we'll draw that downward force of gravity. We're drawing our normal force perpendicular to the surface of the inclined plane. And because it is sliding down a rough surface, there must be friction. And remember, friction is an oppositional force, so it's going to go in the opposite direction of the direction that it's moving. So if this box is sliding down the incline, friction must be pointing up the incline. In our next example, a car is being towed up a hill by a rope. In this example, we have the force of gravity pushing downward, the normal force acting kind of upward and to the left, perpendicular to the surface of the incline. We have friction pointing down the incline, and we have a tension force from the rope pulling the car up the incline. In our last examples, let's draw a free body diagram for the box in each of the two situations below. Suppose an object sits motionless on the ground. Draw the free body diagram for that box. In this case, we have a normal force pushing upward perpendicular to the surface the box is sitting on. And we also have the weight force, the force of gravity, pushing downward. Now, how might that free body diagram change if Monkey Joe is sitting on top of the box? Well, the free body diagram will look just the same except for one additional force. It's still touching the surface, the ground, so there's still a normal force pushing upward. It still has weight, so there's going to be a force of gravity pushing down from the weight of the box, or the mass of the box. But now we also have Monkey Joe as a point of contact, so Monkey Joe's weight force is going to be pushing down on the box, or we could also call that an applied force, which would be equal in size to the weight of Monkey Joe. We will get more practice drawing free body diagrams together in class and identifying what types of forces are present given different situations.